Yeah, I'm excited here to be here to talk to you about Katana Graph and our Graph Intelligence platform, specifically for high performance AI computing. So, just a quick intro to our company. So, we were founded in March of 2020. Dr. Kishab Pingali and Dr. Chris Rosbach are founders from UT Austin, and the key technology innovations that underpin Katana were developed out of their groups over the last 10 years. Farshid Sabed is our Chief Business Officer. He was leading the Edge AI division at Intel before joining Katana. And we have around 85 employees with wide experience both in industry and academia. So why graphs? And Victor did a great job talking about this. And when we look at a lot of the data that our customers have, it has these complex relationships, right, between entities, and these relationships are not easily captured by traditional tabular data structures. And we see this across many verticals, including financial services, life sciences, and cybersecurity. And there's a lot of insight that can be driven from exploiting these relationships between entities. And that's at the core of what our Graph Intelligence platform does, and specifically around Graph AI and Graph ML. So when we look at these domains, so our Graph Intelligence platform sits at the intersection of these graph compute domains. So on the top left, we have a graph database, which is our query engine, right? Uh, Graph AI and machine learning, which we'll go through an example of this today. And then at the bottom, graph analytics and mining, which include graph algorithms such as PageRank and Lavane clustering. And in the context of graph AI, all of these things are very important. Each one of these has a role to play, even if you're just doing graph AI, right? If you think about doing graph database operations to store and manage the data, but also to create new graphs, right? We found that when you're doing graph AI and machine learning, there's a lot of manipulations that need to go into the graph, lots of different data structures and ways to model the data that you can try. And Graph Query plays a fundamental role for that. For graph analytics and mining, when you're developing these graph AI models, a lot of times you can use those algorithms such as PageRank, Lavane clustering, right, as inputs to the to the machine learning model. So we really view, in the context of graph AI, all of these domains is extremely important in trying to achieve that outcome. In terms of our technology differentiation, it can be viewed across these five categories. So the first is speed and size. So Katana Graph has 10x to 100 times faster performance than competing platforms. We handle massive graphs, proven up to 40 billion vertices and 50 billion edges. In terms of scale, the idea is we can scale out and also scale up, right, with new CPU generations. And then another thing that's really important for graph machine learning is our support of heterogeneous hardware. So again, being able to run CPU and GPU workloads on the same platform. Flexibility, again, talking about being able to run these heterogeneous workloads across querying, analytics, and graph AI. They're all very different workloads, but again, they're very important to be able to run all those different types of workloads. We're cloud native, so we support AWS, GCP, and Azure. And then we have the separation of storage and compute, and that's really what enables us to do the scaling up and down on demand. We're open and developer friendly, so we have non-proprietary open Cipher support. We have a Jupyter interface that's data scientist friendly, and we have a deep integration with AI frameworks, including PyTorch Geometric and DGL. Those are really important libraries in machine learning and graph AI specifically. We also support integrations with Databricks, Ray, and Dask. So in terms of applications of the platform, we see benefits across multiple industries and use cases, including, in finance, which is an example we'll go through today. A lot of benefits around fraud detection, AML, customer 360, and then on life sciences, and precision medicine and drug discovery. And then you can see, we have a bunch of other industries and applications here. So really a wide ranging, across industries and applications where you can see this benefit of Graph AI. So for this use case, we're talking about for financial services, and what we're going to talk about is really, an example of Graph AI. We talk about graph neural networks, how they really help this type of problem. So we found that substantial improvement can be made in terms of model accuracy for this credit decisioning model when we use graph neural networks. So this improvement in accuracy translates into fewer defaults in the bank's portfolio, which leads to lower credit expenses. And this is, typically in the order of magnitudes of, millions of dollars when you talk about being able to improve the accuracy of these models. And again, the logic that you're able to reduce the number of defaults in your portfolio, which leads to fewer credit expense, right? Fewer defaults and write-offs. So in this example, we're going to talk about, Abby as a consumer, right? We're a bank and she's applying for a loan and we have her credit history right through the credit bureaus. And this data typically, you think of as tabular data, but it also has a lot of unique relationships in it, right? So in this case, we have Abby and she has 2 trade lines, right? These are 2 existing credits that she has outstanding. She has an auto loan from a credit union, let's say, and then she has a credit card from a bank. But then we also potentially have some information about other individuals that also share those same type of credit trade lines, right? So we're saying Bob has an auto loan, the exact same auto loan as Abby, and it also was originated from this credit union. So our task is going to be able to predict whether or not Abby is a default or a non-default, right? So this is a node classification task. So the main idea behind graph neural networks is this idea of message passing. And this happens in 2 steps. So the first is to aggregate neighboring nodes. So in our example, we have Abby and she has her 2 loans, her auto loan and her credit card. And by performing message passing, our model is going to learn which of these neighboring nodes is most important in predicting if Abby is going to be a bad credit or a good credit. And it's going to learn which of these individual features on the nodes is predictive. So we talk about, the idea that you can encode features from this auto loan. So we have, what type of auto loan it is, what are the balances on that, if it's a high balance, if it's delinquent, all those things, that information we're encoding on this auto loan, as well as the credit card. And so when we do that, we aggregate these 2 features, and then we apply a neural network. So in essence, you're not only getting the benefit of the neural network, which you could get, using a tabular structure, but you're also starting to look at the relationships and the different types of entities that Abby is related to, right? An auto loan, a credit card. If she had several other trade lines, we would be able to aggregate those all together. So we're going to talk about 2 specific ways that GNNs can improve model accuracy. And the first one is this one we kind of touched on, is the GNN's ability to encode high dimensional data. So traditional machine learning relies on modelers to perform feature engineering to aggregate which trade line features are most impactful. So in our example here, a modeler might want to say, okay, how many times within the last 6 months have they had an auto loan that has been 30 plus days delinquent, right? So there's all these different arbitrary windows and things that you have to do to aggregate that data. When you put this data into a GNN, the GNN is essentially automating this feature engineering process, and it's going to be able to learn, which features are most important from these trade lines. So that becomes a really high value add, not just in its ability to predict, but also the time savings, right, for reducing the time spent on feature engineering. And then the second part, reasons why GNNs improve model accuracy is because of their ability to learn from these complex relationships between consumers. So in our example here, we have Abby. We're trying to predict if Abby is going to be a default or not. We also have information in our graph that Bob, who shares a link with Abby, right? They both have the same type of auto loan, originated from the same type of credit union. If Bob is a default, right, that's gonna Abby's proximity, Bob, could be an indicator that she herself might be a default, right? So it's these types of really complicated relationships that the GNN is going to be able to find in the graph. So with that, I'll wrap up. And yeah, if with any questions you have, and I'll turn it back over to Stephen.